Welcome to this solution walkthrough for LeetCode problem number 1503, last moment before all ants fall out of a plank. In this problem, we'll explore how to determine the last possible moment before all ants fall off a plank of length n. Stick around as we break down the problem, discuss the approach, and analyze its efficiency. In this problem, we have a plank of length n units, and there are ants moving either to the left or to the right on this plank. All ants move at a constant speed of 1 unit per second. When two ants meet at the same position, they simply pass through each other without changing direction. The goal is to determine the moment when the last ant falls off the plank, which happens when the ant reaches either end of the plank, position 0 or position n. The input consists of two arrays, left, which contains the starting positions of ants moving to the left, and right, which contains the starting positions of ants moving to the right. Your task is to calculate the time at which the last ant falls off the plank. Now, let's break down the input and output further. The input includes the integer n, which represents the length of the plank and is in the range of 1 to 10,000. The array left contains the positions of ants moving to the left, where each position is between 0 and n, and the size of this array can be up to 10,000. Similarly, the array right contains the positions of ants moving to the right, with the same constraints on its size and values. The output is a single integer representing the time at which the last ant falls off the plank. Let's look at a couple of examples to understand how this works in practice. In the first example, the plank has a length of 4, with ants starting at positions 4, 3, moving left and 0, 1, moving right. The ant at position 4 moves left and falls off at time 4, while the ant at position 3 falls off at time 3. On the other side, the ant at position 0 moves right and falls off immediately at time 0, and the ant at position 1 falls off at time 3. The last ant to fall off is the one that started at position 4, so the output is 4. This illustrates how the problem is all about determining the maximum time any ant takes to reach an edge. In the second example, the plank has a length of 7, and all ants are moving to the right starting at positions 0, 1, 2, 3, 4, 5, 6, 7. The ant at position 0 falls off immediately at time 0, the ant at position 1 falls off at time 1, and so on, until the ant at position 7 falls off at time 7. Since all ants are moving in the same direction, the last ant to fall off is the one that started at position 7, and the output is 7. This example highlights a scenario where all ants are moving in one direction, making the result dependent on the farthest initial position. Finally, let's discuss some constraints and edge cases. The input guarantees that all values in the left and right arrays are unique, and the length of these arrays can be up to 10,000. Importantly, ants pass through each other without changing direction, which simplifies the problem to focusing on the farthest distances they need to travel. In edge cases, if all ants are moving in one direction, the answer will simply be the time taken by the farthest ant to fall off. If there are ants starting at the edges of the plank, they will immediately fall off at time 0. Additionally, if all ants are clustered near one end of the plank, the result will be determined by the ant farthest from the edge they are moving toward. These considerations ensure that the solution is robust across different scenarios. In this problem, we are tasked with finding the last possible moment before all ants fall off a plank of length n. The ants move at a constant speed of 1 unit per second, either to the left or to the right. A critical observation here is that when two ants collide, they simply reverse directions, but this has no net effect on the outcome. This means we can simplify the problem by treating it as if collisions do not occur at all. With this simplification, the key is to determine the time it takes for each ant to reach the edge of the plank. For an ant moving to the left, the time it takes to fall off is equal to its initial position, while for an ant moving to the right, it will take n position seconds. Therefore, the last moment before all ants fall off is simply the maximum time taken by any ant to reach an edge. To solve this, we can consider two approaches: simulating their movements step by step or leveraging the key insight that collisions are irrelevant to directly compute the result. The first approach is a brute force simulation. Here, we simulate the movement of ants step by step, updating their positions and explicitly handling collisions. While this method is conceptually straightforward, it is computationally expensive, with a time complexity of n squared, due to the pairwise collision checks at each time step. This makes it impractical for large inputs, especially since handling collisions is unnecessary given their lack of impact on the outcome. Instead, we can use an optimized analytical approach. By leveraging the observation that collisions can be ignored, we calculate the time for each ant to fall based purely on its direction. For left-moving ants, the time is simply their initial position, and for right-moving ants, it is end position. By iterating through the positions once, we can compute the maximum time among all ants in O(n) time. This method is not only efficient but also avoids unnecessary computations, making it far more suitable for this problem. Based on this comparison, the optimized analytical approach is the clear choice. It simplifies the problem significantly while ensuring optimal performance. Each approach has its trade-offs. The brute force method explicitly models the system and simulates every step, but it is computationally expensive and redundant given the problem's properties. On the other hand, the optimized analytical approach is highly efficient and leverages the key insight that collisions do not matter. This drastically simplifies the solution, reducing the problem to a single maximum computation. By recognizing this property, we achieve an O(n) solution that is both elegant and performant. Ultimately, the optimized approach is the best choice, as it balances clarity, efficiency, and computational feasibility. This method highlights the importance of understanding the problem's core properties to develop an effective solution. To understand this problem, imagine a plank of length n with ants starting at various positions. Each ant moves in either the left or right direction, and when two ants collide, they simply reverse their directions. However, a key observation is that the result of two ants colliding is identical to them just passing through each other. This simplifies the problem significantly because we don't need to track collisions. Instead, we can focus on each ant's movement independently. The last moment an ant falls off the plank depends on its initial position and direction. For an ant moving left, it will fall off the plank after a time equal to its distance to the left edge, and for an ant moving right, it will fall off after a time equal to its distance to the right edge, which is end position. With this insight, the problem boils down to finding the maximum time it takes for any ant to fall off the plank, considering all starting positions and directions. The solution follows a simple three-step process. First, we parse the inputs. This includes reading the plank length n, the positions of the ants, and their movement directions. Next, we simulate the falling times for each ant. We initialize a variable max_time to 0, which will store the maximum time taken by any ant to fall off. For each ant, we check its direction. If it's moving left, the time to fall off is equal to its position, as that's how far it is from the left edge. If it's moving right, the time is end position, the distance to the right edge. At each step, we update max_time with the greater of its current value and the calculated time for the ant. Finally, after processing all ants, we return max_time as the result, which represents the last moment before all ants fall off the plank. The key insight that makes this problem manageable is the simplification of collisions. Since the behavior of ants colliding is equivalent to them passing through each other, we can ignore collisions entirely. This means we only need to consider each ant's starting position and direction to determine the time it takes to fall off. The problem then becomes a straightforward calculation of falling times. By focusing on the maximum time across all ants, we avoid complex simulations and reduce the problem to simple arithmetic and comparisons. To implement this efficiently, we use two input arrays to store the positions and directions of ants, and we maintain a single variable, max_time, to track the largest falling time. This ensures the solution is space efficient, as no additional data structures are needed. Analyzing the algorithm's efficiency, the time complexity is O(k), where k is the number of ants. This is because we iterate through each ant once to compute its falling time and update the maximum. The space complexity is O(1), since we only use a single variable, max_time, in addition to the input arrays. Several edge cases are worth noting. If all ants move in the same direction, the result is simply the maximum distance to the nearest edge. For a single ant, the result is the time it takes for that ant to fall off based on its direction. If multiple ants start at the same position but move in opposite directions, the collision simplification ensures this has no impact. Finally, if there are no ants, the output should be 0, as there's nothing to fall off the plank. Let's walk through an example to see the algorithm in action. Suppose the plank length n is 4, and the ants start at positions 4, 3, 2, 1, with directions L, L, R, R. The first ant at position 4 is moving left, so it falls off after 4 seconds, and max_time is updated to 4. The second ant at position 3 is also moving left, so it falls off after 3 seconds, but max_time remains 4 since 4 is greater than 3. The third ant at position 2 is moving right, so it falls off after 4, 2 equals 2 seconds, and again, max_time remains 4. Finally, the last ant at position 1 is moving right, so it falls off after 4, 1 equals 3 seconds, and max_time remains 4. After processing all ants, the maximum falling time is 4. The final output of the algorithm is max_time equals 4. This means the last moment before all ants fall off the plank is 4 seconds. By leveraging the simplification of collisions and focusing only on the maximum falling time, we've solved the problem efficiently with minimal computation. This approach ensures clarity and handles all edge cases seamlessly, providing a robust solution to the problem. This implementation addresses LeetCode problem number 1503, last moment before all ants fall out of a plank. The goal is to compute the last moment before all ants fall off a plank of length n, given the starting positions of ants moving left, left, and ants moving right, right. The key observation is that collisions between ants do not affect the overall outcome. When two ants collide, they effectively reverse directions, but the result is equivalent to them continuing as if they pass through each other without colliding. This simplifies the problem significantly, as we can consider each ant independently. The function getLastMoment takes 3 inputs: n, the length of the plank; left, a list of positions of ants moving left; and right, a list of positions of ants moving right. Here's how the solution works. 1. Determine the last moment for left-moving ants. These ants fall off the plank at the same position they start from, so the last moment for them is the maximum value in the left list. If there are no ants moving left, left is empty, this value is set to 0. 2. Determine the last moment for right-moving ants. These ants fall off the plank at the position n, and the time it takes for each ant to fall off is n position, where position is the starting position of the ant. The last moment for right-moving ants is therefore n min, right. If there are no ants moving right, right is empty, this value is set to 0. 3. Compute the overall last moment. The final result is the maximum of the last moments for left-moving and right-moving ants, as we are interested in the maximum time before all ants fall off the plank. By considering only the extreme cases, maximum for left-moving ants and minimum for right-moving ants, the algorithm achieves optimal efficiency with a time complexity of O, m plus k, where m and k are the lengths of the left and right lists, respectively. This is the Java implementation of LeetCode problem number 1503, last moment before all ants fall out of a plank. The logic mirrors the Python solution, where we calculate the maximum time for ants moving left and right separately, and then return the maximum of these two values. Key differences include the use of explicit loops for processing arrays in Java's math.max method. The solution avoids unnecessary computations and uses concise, Java-specific syntax. In this example, we have a plank of length 10, with ants moving in both directions. The left array represents ants starting at positions 3 and 7, moving to the left edge of the plank, while the right array represents ants starting at positions 4 and 9, moving to the right edge. To calculate the last moment for the left-moving ants, we identify the farthest position, which is 7. An ant starting at position 7 will take 7 seconds to fall off the plank. For the right-moving ants, their last moment depends on how far the closest ant is from the right edge. The closest ant starts at position 4, so it will take n 4 equals 6 seconds to fall. To determine the overall last moment, we take the maximum of these two values, which is max, 7, 6, equals 7. Therefore, the last ant falls off the plank at time 7. Here, we have a plank of length 5, with all ants moving left. The left array contains positions 0, 1, and 2, while the right array is empty since no ants are moving right. For the left-moving ants, the last moment is determined by the farthest position to the left, which is 2. This means the ant starting at position 2 will take 2 seconds to fall off. Since there are no ants moving to the right, the last moment for right-moving ants is 0. The overall last moment is the maximum of these two values, max, 2, 0, equals 2. Thus, the last ant will fall off the plank at time 2. In this case, we have a plank of length 8, with all ants moving to the right. The right array contains positions 1, 3, and 5, while the left array is empty since no ants are moving left. For the left-moving ants, the last moment is 0 because there are no ants in that direction. For the right-moving ants, the last moment is determined by the closest position to the right edge, which is 1. An ant starting at position 1 will take n1 is equal to 8, 1 equals 7 seconds to fall off. The overall last moment is the maximum of these two values, max, 0, 7, equals 7. Therefore, the last ant falls off the plank at time 7. These examples highlight some key observations about the problem. First, the direction of an ant does not influence other ants because there are no collisions, each ant simply falls off the plank independently. The last moment is determined by the farthest left-moving ant or the farthest distance required for a right-moving ant to reach the edge. If there are no ants in one direction, the last moment for that direction is considered 0. This approach demonstrates how the solution calculates the last moment efficiently, relying only on the extreme positions in the input arrays, rather than simulating the movement of each ant. To analyze the time complexity of this solution, we start by examining the key operations involved. First, we need to find the maximum value in the left list, which represents the farthest distance a left-moving ant must travel to fall off the plank. This is achieved using the max function, which scans all elements of the left list. If the list contains L elements, this operation takes L time. Next, we calculate the minimum value in the right list, representing the closest position to the edge for right-moving ants. Similarly, the min function scans all elements in the right list, and if it contains R elements, this step requires R time. Beyond these, the solution performs a few constant time operations, such as checking if a list is empty, simple arithmetic, and comparing two values. These constant time operations collectively contribute O1 to the total complexity. Now, when we combine these operations, the total time complexity becomes L plus R, where L and R are the lengths of the left and right lists, respectively. However, since the total number of ants is at most n, which is the length of the plank, we know that L plus R is always less than or equal to n. As a result, the time complexity simplifies to n, making the solution very efficient. Turning to space complexity, this solution does not rely on any additional data structures. The left and right lists are part of the input, so they do not count toward extra space usage. The intermediate variables used, such as last_left and last_right, require only a constant amount of memory. Therefore, the overall space complexity is O1, since no additional memory scales with the size of the input. Let us compare this solution to a naive approach. A brute force solution would involve simulating the movement of each ant until it falls off the plank. This would mean iterating over all ants and updating their positions for every unit of time. In the worst-case scenario, with n ants and a plank of length n, this would require n squared time, an inefficient approach for larger inputs. The optimized solution avoids simulation entirely by observing that the last moment any ant falls off the plank depends only on its initial position. For left-moving ants, this is determined by the farthest left position, and for right-moving ants, it is calculated as n minus the farthest right position. By focusing on these key values, the solution reduces time complexity from n squared to n, making it significantly faster. The n time is achieved by performing single linear scans of the left and right lists to find their maximum and minimum values, respectively. Additionally, since no extra data structures are used, the space complexity remains O1, which is highly efficient. Finally, let's consider the best, average, and worst-case scenarios for this solution. In the best case, where all ants are on one side of the plank, either all in the left list or all in the right list, the solution still performs a single scan of the list, resulting in n time. The average case, with ants distributed arbitrarily between the left and right lists, also results in n time because the combined length of the two lists is at most n. Even in the worst case, where both lists together contain exactly n ants, the time complexity remains n, as we still perform just one linear pass over the input. Importantly, the space complexity is O1 in all cases, as the solution does not require any additional memory beyond a constant number of variables. This consistency in performance across all scenarios highlights the efficiency and scalability of the approach. One of the most common mistakes in this problem is incorrectly assuming that ant collisions matter. When two ants collide, they essentially swap directions, but this does not affect the outcome. Each ant continues toward its respective edge, so you can safely ignore collisions. Overcomplicating the problem by simulating these interactions not only wastes time but can also introduce unnecessary bugs. Another frequent mistake is misunderstanding what the problem means by the last moment. Here, it specifically refers to the time it takes for the last ant to fall off the plank, not the positions of the ants or any midpoint they might pass. Lastly, a significant inefficiency arises when people try to sort the ants' positions to determine the order in which they fall. Sorting increases the time complexity to O n log n, but the last moment can be calculated in O n by simply focusing on the farthest distances ants travel to the edge, depending on their direction. Additionally, it's important to remember edge cases, such as when all ants move in the same direction, either all to the left or all to the right. Forgetting these cases can lead to incorrect results if your implementation doesn't handle them explicitly. Another common oversight is confusing the plank length, n, with an array index. Remember, the plank length represents the boundary, not a zero-based index. Ants fall off the plank when their position becomes less than 0 for left-moving ants or greater than n for right-moving ants. Misinterpreting this can cause logical errors in your solution, so it's essential to use the plank length properly as the maximum positional boundary. Now, let's highlight some key insights for tackling this problem effectively. The most critical realization is that collisions between ants don't matter. You can treat each ant as an independent particle moving either left or right. This allows you to focus solely on the farthest distances ants travel to the plank's edges. Specifically, the last moment when any ant falls off is simply the maximum of two values, the farthest distance for left-moving ants and the farthest distance for right-moving ants. It's also crucial to communicate this simplification clearly to your interviewer, as it demonstrates your ability to strip down a problem to its core essentials. Be prepared for follow-up variations, such as calculating the total time for all ants to fall or adapting the solution to a plank with a curved or irregular shape. These variations test your ability to generalize the logic and deal with new constraints. This problem also shares similarities with a few related LeetCode problems that can help you build a deeper understanding. For instance, LeetCode 1029, two-city scheduling, involves optimizing the distribution of groups, which is conceptually similar to splitting the ants' movement into left and right directions. LeetCode 573, squirrel simulation, is another optimization problem that deals with minimizing or maximizing distances to edges. Similarly, LeetCode 874, walking robot simulation, focuses on movement and boundary constraints, making it a good exercise for understanding movement dynamics. Finally, LeetCode 1267, count servers that communicate, involves analyzing independent movements and their interactions, which parallels the idea of ants moving independently without collisions impacting the final outcome. Practicing these problems can help reinforce the concepts and techniques required for this challenge. There are also several approaches you can take to solve this problem, each with varying levels of efficiency. One option is the simulation approach, where you simulate the movement of each ant step by step, accounting for collisions. While this method is straightforward to implement, it's highly inefficient, with a time complexity of O n squared, or worse due to collision handling, making it overkill for this problem. A much better approach is to use mathematical boundaries. For left-moving ants, the last moment corresponds to the maximum of their initial positions. For right-moving ants, it's the plank length n minus the minimum of their initial positions. Combining these two results gives the global maximum, solving the problem in O n. Finally, you might consider a binary search approach, where you calculate the last moment using iterative checks. However, binary search adds unnecessary complexity to a problem that can already be solved optimally in linear time, making it an inefficient choice for this scenario. Thank you for watching. In this session, we summarized the problem and broke it down to a simple yet efficient solution. Hopefully, you gained insights into how to approach problems like this. Be sure to share your thoughts and subscribe for more coding content. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!